The cabin was warm. That was the part no one could explain. 3 feet of snow had fallen in less than 36 hours. The kind of storm that bends pine trees sideways and turns wagon trails into white walls. Temperatures had dropped to single digits overnight, and by morning, 2 families on the ridge had abandoned their shelters and walked, nearly half a mile through the dark, to take refuge with neighbors. But not her. Her cabin held. And when the men from the settlement came to check on her the following afternoon, half expecting to find the roof collapsed under the weight or the fire long dead, they found smoke curling steadily from the chimney. They found the doors swinging open without a creak. And they found her inside, dry, unhurried, tending a fire that hadn't needed to burn hard all night. What they saw on the roof stopped them cold. It wasn't planks. It wasn't bark shingles. It wasn't anything they recognized as a proper roof at all. It was a dense weave of branches, alder, willow, young birch, layered and laced together over the rafters in a pattern that looked, to their eyes, almost desperate. Almost like the work of someone who had simply run out of options. One of the men said it out loud. That thing should have caved in. He wasn't wrong to think so. By every rule of common sense they carried with them into that wilderness, a woven branch roof under 3 feet of wet snow should have buckled, should have flooded the interior, should have been the last mistake of a woman building alone and too late in the season. Instead, it had done something none of them expected, something the snow itself had made possible. The secret wasn't in what she had built despite the winter. The secret was in what the winter had built for her, layer by silent layer, through the night, on top of that improbable roof. And once you understand what was happening up there, in that compressed space between woven branches and frozen sky, you will never look at a snowstorm the same way again. If you want to follow along as we break down exactly how this worked, and why it worked better than a standard plank roof in those conditions, make sure you're subscribed. And drop a comment below. Where in the world are you watching from? We read every single one. The autumn of 1871 arrived early in the upper valleys of the northern frontier. Local accounts from that region describe it as one of the shortest building seasons in recent memory. Frost appearing on the ground before the last wagon trains had finished their runs, and the first hard freeze arriving nearly 3 weeks ahead of what settlers had come to expect. For most families on the ridge, that wasn't a disaster. They had arrived in spring or early summer. Their cabins were already standing, roofed, chinked, and stocked. They had had months to prepare. Edna Marsh had not. She had come alone, widowed 2 years prior, with a land claim filed at her own name under the homestead provisions, arriving in late September with a single mule, a small iron stove, 2 trunks of tools and dry goods, and a plot of mixed timberland on the eastern slope. She was 41 years old, and she had precisely 6 weeks, by her own estimate, before the weather made outdoor construction impossible. She moved fast. The log walls went up in under 3 weeks. She was no stranger to hard labor, and oral accounts passed through that community describe her as someone who worked from first light until she could no longer see the notches she was cutting. The foundation stones were set. The door frame was fitted. The stove was centered and the flue rough cut through the wall. Then she looked at what remained of her lumber, and she did the arithmetic. She was short, not by a little, by a significant margin. The planks she had hauled up the slope were enough for a partial roof at best, and the nearest sawmill was 2 days' travel each way. There was no time. There was no money to spare for a second haul. And there was, by every reasonable measure, no good solution available to her before the weather closed in. What she did next, the men of the settlement would later describe as either brave or foolish, depending on which side of that winter they were standing on when they told the story. She walked into the tree line with a hatchet and a length of rope. For the next 4 days, Edna cut and hauled branches. Not logs, branches. Young, flexible growth from alder and willow stands near the creek bed, along with longer runners of birch she could strip and bend without splitting. She selected them with care, oral history's note, favoring pieces between 1 and 2 inches in diameter, thick enough to bear weight, supple enough to weave without cracking. She laid the first layer across the rafters lengthwise, lashing each piece at both ends. Then she laid a second layer crosswise, weaving it down through the first over and under, the way a person might weave a basket, except the basket was 12 feet wide and 20 feet long, and it had a hold against whatever the sky decided to send. When she was finished, she stood back and looked at it. It was not beautiful. It was not reassuring. It was a patchwork of bare branches against a gray October sky, gaps visible between the weave wide enough to slip a hand through in places. Light came through. Wind came through. And when the first light rain fell 2 days after she finished, a thin mist of it came through too, speckling the dirt floor inside. A neighbor who had ridden up to check on her progress, a man named Callum Fergus, who ran cattle on the adjacent claim, pulled his horse to a stop, looked at the roof for a long moment, and said nothing for a while. Then he said, "You planning to sleep under that?" Edna said she was. He rode back down the slope without another word. But local oral accounts agree on what he told his wife that evening, that the widow Marsh had lost her nerve or her mind, and that someone would probably need to go collect her before Christmas. He was not being cruel. He was being practical, in the way that frontier people were practical, measuring everything against the probability of survival. And by every measurement he knew, a woven branch roof in a northern winter was not a roof at all. It was a mistake waiting to be buried. The first real snowfall came the 3rd week of November. It arrived the way serious snow arrives in high country, not as a polite dusting, but as a sustained, windless curtain of white that fell steadily for nearly 18 hours without pause. By the time it stopped, somewhere between 14 and 16 inches had accumulated across the ridge. Heavy, wet snow, the kind that compresses under its own weight and holds its shape like packed clay. Edna was inside when it started. She kept the stove low, rationing her wood, and listened to the silence that comes when snow swallows all sound from the outside world. At some point in the night, she heard the roof creak, then settle, then creak again. She did not sleep much, but in the morning, the roof was still there. More than that, it had changed. What had been an open weave of bare branches the night before had become something else entirely. The snow had not fallen through the gaps as she had feared. It had bridged them. The flakes had caught on the branches, compacted against each other, and sealed the spaces between the weave from the outside in. The way ice forms across the surface of a river, locking layer to layer until the whole surface becomes a single continuous skin. By the time Edna stepped outside and looked up, she was not looking at a flawed roof anymore. She was looking at a vault. The woven branches had become the skeleton, and the snow had become the body. The two materials, rigid wood and compressible ice crystal, had done together what neither could have done alone. The branches held the snow in place against the slope of the roof. The snow sealed the branches against wind and water infiltration, and the resulting composite layer, roughly 8 to 10 inches of packed snow sitting on top of 3 to 4 inches of interlaced branch, had a combined thermal resistance that no one on that ridge, including Edna herself, had calculated in advance. What was happening, in physical terms, was straightforward, even if the settlers had no language for it at the time. Snow is one of nature's most effective insulating materials. This is not intuitive. Snow is cold. Snow is associated with the lethal end of the temperature spectrum. But snow in its packed, layered form is approximately 90 to 95% trapped air by volume. And trapped air, still enclosed, unable to circulate, is precisely what stops heat from moving. It is the same principle behind wool, behind down feathers, behind the thick fur of an animal in winter. The insulating power is not in the material itself. It is in the air the material captures and holds motionless. On a standard plank roof of the period, snow was a hazard and a burden. It added weight. It found cracks. It melted against the warm underside of the boards and refroze at the eaves, working its way into any weakness in the structure over time. Settlers shoveled it off when they could. They built steep pitches to shed it. They treated it as an enemy to be expelled. Edna's woven roof did something different. It held the snow in place, not because she had planned it that way, but because the geometry of the weave gave the snow something to grip. And in holding it, the roof turned it into armor. Inside the cabin, something measurable was happening. The temperature differential between the interior air near the ceiling and the exterior air above the roof which on a plank cabin of similar size might have been bridged by 6 to 8 inches of wood and air gap, was now bridged by a composite layer nearly 14 inches thick, with a thermal resistance closer to that of a tightly packed straw roof than a standard board and batten construction. Oral account from that winter suggests that Edna's morning fire, the one she lit to take the chill off the cabin after a cold night, was noticeably shorter in duration than what her neighbors described in their own shelters. Where Callum Fergus reported burning wood for 2 to 3 hours each morning before his interior reached a comfortable working temperature, Edna's fire was reportedly burning for 45 minutes to an hour before she shed her outer layer. She noticed it. She recorded it in her own way, a series of tally marks in the back of a ledger book that survived and was later described by a local historical society archivist as evidence of a woman keeping careful track of her fuel consumption through the winter. She had started the season believing she had barely enough wood to survive. By mid-December, she realized she had more than enough. Edna Marsh had never attended a university. She had never read a paper on thermodynamics. She almost certainly had never encountered the word conductivity in any formal context. But she had spent 41 years paying attention to the physical world, to what kept things warm and what let warmth escape, to what survived a hard winter and what didn't, to the difference between a wall that held and a wall that failed. And what she had built, without knowing its name, was a system of layered thermal resistance that engineers of a later era would have recognized immediately. Let's slow down and understand what was actually happening inside that roof. Heat moves in 3 ways: conduction, convection, and radiation. In a winter shelter, the enemy is primarily conduction, the direct transfer of heat from a warm surface to a cold one through physical contact. A single plank of pine, 6 inches thick, conducts heat reasonably well. It's a solid material, and solid materials, generally speaking, allow heat to travel through them. Wood is better than stone, better than iron, but it is not a great insulator on its own. Under extreme cold, a wood roof alone is not enough to prevent steady, significant heat loss through the ceiling plane. What stops conduction is not density. It is discontinuity. It is the interruption of direct contact, the introduction of a barrier that forces heat to work much harder to cross from one side to the other. Edna's woven branch layer did this at the first level. The branches were not a solid surface. They were a lattice, dozens of individual contact points separated by open space. Heat rising from the interior of the cabin met the underside of the branches and was forced to navigate a fragmented surface rather than a continuous one. The rate of conductive transfer dropped immediately compared to a solid wood roof of equivalent thickness. Then the snow arrived and raised that effect by an order of magnitude. Packed snow, as noted, is roughly 90 to 95% air by volume. The ice crystals that form its structure are connected, but tenuously, separated by microscopic pockets of still air that act as individual insulating cells. When heat attempts to conduct through packed snow, it must cross an almost incomprehensible number of these tiny barriers in sequence. The result is a material with a thermal conductivity value, the measurement of how readily it transfers heat, that is dramatically lower than wood, lower than most natural building materials, and comparable in some conditions to purpose-made insulation product developed in the 20th century. The combination of woven branches below and packed snow above created what modern builders would recognize as a multi-layer insulating assembly. Each layer had different physical properties. Each layer addressed a different mechanism of heat loss. Together, they created a thermal barrier across the ceiling plane that was far more effective than either material alone, and far more effective than the single-layer plank roofs that surrounded it on the ridge. There was a second effect, less obvious but equally important. The airspace trapped between the branch weave and the underside of the snowpack was not moving. In a standard plank roof with a gap beneath the boards, cold air could infiltrate from the eaves, circulate within the roof cavity, and carry warmth away through convective exchange. Edna's weave had no such gap. The snow sat directly on the branches, compressing them slightly and closing any significant air channel. The air that remained between the two layers was static, locked in place, unable to circulate. Static air, is the gold standard of insulation. It is what every insulating material, from animal fur to modern fiberglass bats, is ultimately trying to achieve. The moment air starts moving, it carries heat with it. The moment it stops, it becomes a barrier. Edna had stopped the air without knowing that was what she was doing. A rough estimate, grounded in the physical properties of the materials involved, a composite roof assembly of this type, 4 inches of interlaced hardwood branch plus 8 to 10 inches of compacted snow, would produce an insulating value in the range of R10 to R15 under stable winter conditions. A standard 6-inch plank roof of the era, without snow retention, would produce something closer to R5 to R7. The difference, in practical terms, was the difference between a fire that burned all night and a fire that was banked by 10 o'clock and still holding warmth by dawn. It was not magic. It was geometry, material science, and the accidental genius of a woman who had simply run out of other options. January brought the test that no one had asked for, and everyone on the ridge received equally. A polar air mass descended from the north over the course of 3 days in the second week of the month, the kind of sustained cold event that local oral accounts from that period describe, with a particular kind of reverence, the way people speak about something they survived but did not entirely understand. Temperatures dropped to minus 18 degrees Fahrenheit on the coldest night. Wind came with it. Not a gale, but a steady, cutting north wind that found every gap in every wall on that ridge and worked its way through without apology. It was the kind of cold that makes wood contract and crack audibly in the night. The kind of cold that freezes the water in a bucket left near a door that hasn't been open in hours. The kind of cold that turns a poorly built shelter from a temporary inconvenience into a genuine, immediate danger. The ridge had 8 occupied cabins that winter. Of those 8, local accounts indicate that at least 4 experienced significant heat loss during that cold snap. Fires burning through the night and struggling to maintain interior temperatures above 40 degrees Fahrenheit by early morning. 2 families reported ice forming on the interior walls near the floor. 1 family burned their last cord of stored wood during those 3 days and had to begin cutting green timber in below zero temperatures to maintain any heat at all. Callum Fergus later told the story himself, and it was recorded in a community memoir compiled in the 1890s. He said he woke at roughly 3 in the morning on the worst night of that cold event. The fire in his cabin had burned low, not out, but low, and the interior temperature had dropped enough that his breath was visible even near the center of the room. He spent the rest of the night feeding the fire at intervals of 45 minutes, never allowing himself to sleep fully, because he did not trust the structure to hold warmth without constant input. By his own account, he burned close to a full cord of wood in those 3 days. A cord is a substantial unit, a stack 4 feet high, 4 feet wide, and 8 feet long. And burning one in 72 hours in a small single-room cabin represents a rate of fuel consumption that, extended across a full winter, would have left most families short of fuel before spring. Edna's consumption during that same period, as reconstructed from her ledger tally marks and later described by the historical archivist, was markedly different. She had banked her fire each night, reducing it to coals rather than maintaining an active flame. And her interior temperature, by her own account recorded in the ledger, had not dropped below what she described as comfortable for sleep without extra covering. She burned, by rough estimate derived from her tally system, somewhere between 1/4 and 1/3 of what Fergus burned during the same event. The reason was the roof. While the plank roofs on the other cabins radiated heat skyward at a rate governed by the thermal conductivity of dry pine, losing somewhere between 30 and 40% of a small cabin's total heat through the ceiling plane in extreme cold, Edna's composite assembly was doing something categorically different. The snow pack above the branch weave had thickened through January to nearly 14 inches in places. The insulating value of the assembly had increased as the season deepened. The ceiling plane of her cabin had become, in effect, a thermal lid, slowing the rate of heat escape to a fraction of what the surrounding structures were experiencing. In concrete terms, while her neighbors' cabins might shed heat fast enough to require active fire management through the night, Edna's cabin retained enough stored warmth from a well-built evening fire that the interior temperature, measured against the outside air, dropped by an estimated 15 to 20 degrees Fahrenheit less than the standard plain cabins over an 8-hour period. That gap, 15 to 20 degrees across a single night, is not a minor comfort difference. In a winter at -18 outside, it is the difference between waking up cold and waking up in danger. It is the difference between a fire you tend and a fire you pray doesn't go out. The coldest night of the season passed. Morning came. Edna opened her door, looked out at the white stillness of the ridge, and put a kettle on. She wasn't thinking about physics. She was thinking about breakfast. But outside, on a slope where 4 families had spent the night fighting their own fires, the snow on her roof sat thick and undisturbed, and the smoke rising from her chimney was thin and unhurried, the smoke of a fire that had nothing left to prove. Callum Fergus was not a man who asked for help easily. Oral account from that community paint a consistent picture of him. A Scots-Irish cattleman in his late 40s, deliberate in speech, economical in expression, and constitutionally reluctant to admit that another person, particularly a woman homesteading alone, might know something he did not. He had come to that ridge with 15 years of frontier experience behind him. He had built 2 cabins before this one. He had wintered in hard country and survived it without any unusual arrangements. He was also, by the second week of February, running critically low on firewood. The cold snap in January had hit his reserves harder than he had anticipated. He had burned through his stored cord in a half faster than any previous winter on record for him, and the green wood he had cut in desperation during the cold event was still too wet to burn cleanly, producing more smoke than heat and leaving a creosote buildup in his flue that worried him every time he fed the fire. His interior walls were showing frost damage near the floor. His livestock, sheltered in a lean-to off the back of the cabin, were consuming more feed than projected because their bodies were working harder against the cold. He rode up to Edna's claim on a Tuesday morning in the 3rd week of February. He did not say he was in trouble. He said he was in the area and thought he would check on her. He dismounted, tied his horse, and stood in her dooryard for a moment, looking at the roof the way a man looks at something he has been thinking about for longer than he intends to admit. The snow on it was remarkable, not for its volume, though it was thick, compressed into a dense white cap nearly 16 inches deep across the center span, but for its evenness. On every other roof on the ridge, snow was an irregular presence, thick where the wind had drifted it, thin where the pitch had shed it, absent in patches where the warmth escaping from below had melted it from the underside. On Edna's woven roof, the snow sat level, continuous, and undisturbed. There were no melt patches, no bare spots, no evidence of interior heat punching through the surface. That last detail was the one that mattered most, though Fergus would not have been able to articulate why at the time. He only knew that it looked different, and that her woodpile, stacked neatly against the east wall, looked substantially less diminished than his own. She invited him inside. The cabin was warm, not aggressively so, not the roaring heat of a fire burning in desperation, but the quiet, even warmth of a space that had simply held its temperature through the night with modest fuel input. The stove held a low, steady burn. The air near the ceiling, he noted, was noticeably warmer than in his own cabin, where cold radiated downward from the plank roof and created a temperature gradient that made the upper half of the room comfortable and the lower half perpetually chill. He stayed for 2 hours. They talked about the winter, about the cold snap, about wood consumption. Edna did not volunteer information about her roof design in any instructional way. She answered what he asked directly, and what he asked, eventually, was simple. How much wood have you burned since November? She showed him the ledger. He looked at the tally marks for a long time without speaking. Then he looked up at the ceiling, at the underside of the woven branches above him, the bark still on, the lashings still tight, and he was quiet for another moment. He left without further comment on the subject. He did not say she had been right and he had been wrong. He did not say anything that could be recorded as an admission. But the community memoir that compiled these accounts decades later notes a single corroborating detail, that in the spring of 1872, Callum Fergus dismantled the plank roof on his cattle barn and replaced it with a woven branch structure modeled closely on what Edna had built, lashing alder runners across the existing rafters and leaving the assembly open to the first snowfall of the following autumn. He never explained his reasoning to anyone who wrote it down. He didn't have to. The roof explained it for him every winter for the next 11 years, until he sold the claim and moved south. One by one, quietly and without ceremony, 3 other families on that ridge made similar modifications to their outbuildings over the following 2 seasons. None of them called it technique. None of them gave it a name. They simply did what the evidence in front of them suggested was worth doing. The way frontier people absorbed useful knowledge, not through argument or persuasion, but through observation and outcome. The woman who had built wrong had, without intending to, built a school. By the spring of 1873, Edna Marsh had been living under her woven branch roof for 2 full winters. The structure had not collapsed. It had not flooded the interior during the spring melt. It had not rotted through or been compromised by the freeze-thaw cycles that destroy conventional roofing materials from the inside out. In fact, when she climbed up in April to inspect it, pulling herself onto the roof with a rope tied to the ridge beam, she found something she had not fully anticipated. The branches at the core of the weave were in better condition than the outermost layer of planks on her neighbor's cabin. This was not accidental. It was the result of 2 physical dynamics that worked in her favor, both of them hidden from casual observation. The first was moisture management. A conventional plank roof of the era had a fundamental problem that its builders rarely discussed openly. It was a single rigid layer, and rigid layers crack. Wood expands when it absorbs moisture and contracts when it dries. Through repeated freeze-thaw cycles across a single winter, a plank roof experiences dozens of these micro-expansions and contractions, and each one opens the material a fraction more than before. By the 3rd or 4th winter, most plank roofs on the northern frontier had developed enough checking and gapping to allow meaningful moisture infiltration, accelerating decay from the top surface downward. Edna's woven assembly had no such problem. The individual branches were small in diameter, between 1 and 2 inches, which meant their moisture content equalized quickly with the surrounding environment. They expanded and contracted too, but their small cross-section meant the dimensional change was minimal in absolute terms. More importantly, the weave itself was a flexible structure. Where a rigid plank would crack under stress, the woven assembly simply shifted, redistributing load across dozens of contact points rather than concentrating it at a single weak joint. This is a principle that structural engineers would later formalize under the concept of load distribution in flexible assemblies. But it was also something that basket weavers, wickerwork craftspeople, and indigenous builders across multiple continents had understood empirically for centuries before the word engineering existed in its modern sense. The Ainu people of northern Japan built structural elements from woven materials that survived decades of severe winter loading. Scandinavian turf roof builders used woven branch underlayers, called vidger in some regional traditions, as the flexible skeleton beneath packed earth and sod, precisely because the weave could absorb differential movement without failure. Edna had arrived at the same solution independently, driven by the same constraint that had driven builders across the northern world for thousands of years: not enough rigid material and too much winter to survive without a roof. The second dynamic was snow load distribution. A plank roof under heavy snow loading behaves as a series of individual beams, each carrying its share of the load and bending. Under extreme loads, the weakest plank fails first, and when one fails, the load redistributes to its neighbors, potentially triggering a cascade. This is why catastrophic roof collapses under snow load tend to be sudden and total rather than gradual and partial. A woven branch assembly under the same load behaves differently. Each branch in the weave contacts its neighbors at multiple points. Load applied to any section of the roof is immediately shared across a network of interconnected elements. Not just the 2 or 3 planks directly beneath the load, but the entire woven matrix radiating outward from that point. The structure acts less like a series of beams and more like a tension net, and nets, as anyone who has seen a hammock hold a sleeping person knows, are extraordinarily efficient at distributing weight across a wide area. Local oral accounts suggest that in the winter of 1873, which brought a late-season snowfall heavy enough to collapse a tool shed on the Fergus claim, Edna's roof carried a snow load estimated at between 35 and 45 pounds per square foot without visible deflection. A rough calculation puts the total weight on her approximately 240 square foot roof surface at somewhere between 8,000 and 11,000 pounds. The woven branch assembly, reinforced by 2 seasons of compaction and minor repairs, held it without incident. As for longevity, the core structure of Edna's original weave lasted, with seasonal maintenance, for approximately 7 years before requiring substantial replacement. Each spring, she walked the roof and replaced branches that had become brittle or had broken under the previous winter's load, a process she described in ledger notes as taking between 1 and 2 days per season. The replacement material cost her nothing but the labor of cutting it. A plank roof of the period, properly maintained, might last 15 to 20 years, but required milled lumber for repairs, a recurring cost that frontier families felt acutely. Edna's roof required only time and the same forest that surrounded her on all sides. In the calculus of frontier survival, that was not a small distinction. It was the difference between a maintenance task you could always perform and one that depended on money, supply chains, and the goodwill of a sawmill operator 2 days away. There is a particular kind of irony embedded in the history of building technology. Progress, as it is usually understood, moves in one direction, from primitive to sophisticated, from inadequate to optimized, from the makeshift solutions of desperate people toward the engineered certainty of professionals who have studied the problem. The story we tell ourselves about construction is a story of improvement, better materials, better tools, better understanding of the forces involved. What that story tends to leave out is the cost of rigidity. Modern residential roofing is, almost without exception, designed to shed snow. The steep pitches of contemporary mountain architecture, the slick surfaces of metal roofing panels, the smooth asphalt shingles engineered for rapid water runoff, all of it is optimized around a single premise. Snow is a burden to be expelled as quickly as possible. Get off the roof. Get on the ground. Keep the structure clear. This approach is not wrong exactly. For the lightweight framing systems that dominate modern construction, engineered lumber, trusses designed to minimum load specifications, insulation placed inside the ceiling cavity rather than above it. A retained snow load is a genuine structural risk. The roofs are not built to carry it. But in eliminating the snow load, modern construction also eliminated the insulating benefit. A well-insulated modern roof, properly air-sealed, with 12 or more inches of blown-in insulation in the attic cavity, achieves insulating values in the range of R38 to R60, depending on the material used and the thickness of the installation. This is significantly better than Edna's composite assembly in raw thermal resistance terms. There is no question that modern insulation technology, when properly installed, outperforms packed snow. The question worth asking is, how often is it properly installed? Studies of existing residential housing stock in cold climate regions of the United States consistently find that a substantial proportion of homes, estimates in various surveys range from 40 to 60%, have attic insulation that is either insufficient in depth, compromised by air leakage around penetrations, or degraded by moisture infiltration over time. The theoretical R value of the installed material and the actual thermal performance of the assembly and service are frequently not the same number. Edna's roof had no such gap between theory and practice. The snow that insulated her cabin was always exactly as thick as it was, performing exactly as the laws of physics dictated, renewed and refreshed by each successive storm. It required no installation. It cannot be poorly specified or incorrectly applied. It arrived on its own, settled into place, and did its work without supervision. There are traditions across the northern world that understood this principle and built around it deliberately. In parts of Scandinavia, traditional turf roofs, torvtak in Norwegian, used a woven branch or birch bark underlayer beneath packed earth and grass sod, creating a composite assembly that retained winter snow as an additional insulating layer above the sod. These roofs, in their traditional form, could achieve effective winter insulating values comparable to modern mid-grade insulation, not through technological sophistication, but through the intelligent use of what the environment provided for free. In Siberia, indigenous builders of semi-subterranean winter shelters understood that the worst thing a roof could do in winter was lose the snow that fell on it. Their structures were designed with low pitches and rough surface textures specifically to retain accumulation. The snow was not incidental to the design. It was load-bearing, thermally active, and anticipated from the first day of construction. The Ainu of Hokkaido, whose traditional chai's dwellings used thatched reed roofs over a woven structural underlayer, observed that a thick winter snow cover extended the effective heating season of their shelters by weeks, reducing fuel consumption in a landscape where fuel was gathered by hand and every cord of wood represented days of labor. Edna Marsh knew none of this. She had not studied Arctic architecture or Scandinavian vernacular building traditions. She had arrived at the same conclusion through the same pressure that had driven every one of those traditions: a brutal environment, insufficient conventional materials, and no option but to work with what was available. What she built was not primitive. It was not a stopgap or a failure she made the best of. It was a thermally coherent system, flexible, self-renewing, and precisely adapted to the specific conditions of her site, her climate, and her resource constraints. It was, by any honest measure, better suited to its environment than the plank roofs that surrounded it. The difference between her approach and theirs was not intelligence or preparation. It was assumption. Her neighbors assumed that a proper roof expelled snow. Edna, without the materials to build a proper roof, discovered that a different kind of roof could use snow instead. And in that discovery, accidental, unglamorous, made in desperation on a cold October afternoon with a hatchet and a rope, was the quiet truth that has always lived at the center of vernacular engineering. The best solution is rarely the most conventional one. It is the one that understands what the environment is actually offering and builds accordingly. Edna Marsh spent 11 more winters on that ridge before filing a transfer of claim in 1882. Every one of those winters, her roof held. Every one of those winters, her woodpile lasted. And every spring, she climbed up with a rope and a hatchet and replaced what needed replacing, walking the surface of a roof that had been called a mistake, cutting out the brittle pieces, weaving in the new growth, and leaving the rest exactly as it was. Because the rest was still working. This content is produced for historical and educational storytelling purposes only. It does not constitute structural or engineering advice. Always consult qualified professionals before attempting any construction project.